talking about equivalent systems. So, and this is the last session we will have on equivalent systems. I want to do more problems, and that will lay the foundation for the next topic, right? So what is an equivalent system? As we have discussed, basically an equivalent system means what? You have a structure, you have an object with several forces or moments acting on that, and you're typically asked one of these two questions, right? One is find, okay, or given. Actually, this is the first part. The first case is that given a point, move all forces and moments. You may also have free moments or couples, right? Okay, to that point. Or sometimes you're asked, okay, find a point in such a way that if you move all forces and moments there, okay, there won't be any moment. Both are the same concept, okay? Which means that you want to replace all the given forces or moments that are acting on a rigid body with a single force or a single force and a single moment, okay? The steps are basically the same. There are two steps involved. The steps are as follows. Step one, you just simply move all forces to this new point. What does that mean? That means find the resultant of all forces and place it there. Okay. The second step, once you move those forces, you have to pay a penalty. When you move those forces to the new location, you pay a penalty. The penalty is that you need to find some of the moment or moments of all forces about this point. Also, okay, add any applied moment or any applied couple to this sum and place it there. Okay. So what I want to do, I would do three problems that basically demonstrate to you how this concept is basically working. And I will do problems of both types, and both 2D and 3D. So let's start with a 2D problem. The 2D problem is this. Let's assume you're given this beam, a straight beam. Of course, we haven't discussed what a beam is yet, but this is a beam structure. And all these dimensions are given, 2 feet, 4 feet, 2 meters, 4 meters, and 2 meters. You have an applied load here, 2.5 kilonewton, and the slope of this is 3, 4, 5. You have another force acting here, making an angle of 30 degrees with a vertical line, and the magnitude of that force is 1.5 kilonewton. And then another force of 3 kilonewton acting downward, and then somewhere along this structure, maybe at this point, you also have a couple, a free moment of, say, 5 kilonewton meter applied. So this is given. What the problem is asking is that, okay, move all forces and moments to point A. In other words, we want to replace all of these with a single moment and a single force acting at point A. So what is the procedure? Step number one, step one, you want to find resultant of all these and move it to that point A. What does that mean? You need to find summation of all these forces along X, summation of forces along Y, add them all up, and put it there. That means find the resultant. How do you find the resultant? Remember, in general, never forget, anytime you have an inclined force, resolve it to its components, right? So this is 4/5 of 2.5, so this is 2 kilonewton. This 3/5, 1.5 kilonewton. This is 1.5 cosine of 30 degrees, which is square root of 3/2, so it is 0.75 square root 3, which should be about 1.3 kilonewton. And then you have sine of 30 times 1.5, so this is 0.75 kilonewton. So resolve them into their components, then add them all up, find the resultant. Sum of the forces along X is what? If this is X, this is Y, you have negative 0.75 kilonewton. You have, you have positive 0.75. You have negative 2 kilonewton, and that's it. That's all you have. So you have negative 1.25 kilonewton force along X. How about Y? All forces are acting downward, so that means you have negative 3 kilonewton. You have negative 1.3 kilonewton, and you have negative 1.5 kilonewton, and that's it. So the total is 2.8, negative 5.8, right? Negative 5.8 kilonewton. This is the resultant of all these forces. Any questions?
Yeah, I have a question. For the second force, the 1.5 kilonewton at 30 degrees.
This one?
Yeah. How did the X component? Would it be sine 30?
The X component would be sine 30, so sine 30 is 1/2, so it would be half of 1.5, which is 0.75.
Okay.
Right, yes.
Does the beam not have mass, or like we?
No, we ignore that as the mass of the structure. Good question. Any other questions? These are all the applied forces that have been given. So that means now this was the structure. So I just simply move all those forces there. So in other words, get rid of all of these, move them there, and which means I have a force of 1.25 kilonewton here, and a force of 5.8 kilonewton. You can do that as long as you add the effect of moving these forces there. And that penalty is what? That you need to find the moment of each force, add them all up, add also the applied moment to it, put all those moments here. So you need to find the sum of the moments about point A, add them all up, that means moment of all forces about point A, add this moment to it, put that single moment there. So that would be what? Moment of this force about point A is 3 times the vertical distance between the two, and it's clockwise, so it would be negative 3 times 8, right? That's the distance. Negative 3 kilonewton times 8 meters. This force has two components. This component does not make any moment about point A because it is going through that point, right? Whenever you have a force, you want to find its moment about a point that is acting along the line of action of the force. That is 0, because there is no distance between that point and the line of action of the force. Okay? So the moment of this force, and this force about A is 0. We only have these two, and that is points, that 1.3 acting clockwise at a distance of 6. So you have negative 1.3 times 6. And then for this one, you have 1.5, negative 1.5 times 2. Okay? You also have another moment, which is the applied moment, and that is this one, acting counterclockwise, so that is positive. So you have 5 kilonewton meter also. Add all of these up, put it at point A. And that would be what? You have negative 24, negative 7.8, negative 3, plus 5. So that would be 29.8, right? Kilonewton meter. That is at A. So all you need to do, just add a moment of 29.8 kilonewton meter clockwise to that point. So this system of forces and moments does exactly the same function as all these forces and this moment do individually. Okay, that is the meaning of an equivalent system. Okay, any questions? Yes.
When we're writing our answer, do you want us to do that arrow or just a positive or negative?
Either one, either one. This is redundant, really. If I put negative, I don't have to put this one, but I put both. But you don't have to do both. Yes?
So because the moments, the x component moments run through A, you don't need that. It would be
Correct, because when the force passes through a point, the moment of that force about that point is always 0. Right. Let's do another problem. And this second problem would be a 3D problem. Right? I'll do the same concept applies in 3D. Same procedure. So I'm just going to erase this part. No. Let's say you have a problem like this. X, Y, Z in this problem are given like this. You have a pole, A, O. This pole, a cable, and the height of this pole is given, 8 meters. A cable is attached from A to point B. Coordinates of B are given. It lies along a y-axis, so it has 0, 6, and 0. This distance is 6 meters. Okay. And another cable is attached to point C, which is at a height of 6 meters, to a point D. Point D, coordinates of point D are given x2, y of -3, and height of 0, obviously, because it resides on xy plane. Problem states that a force of 5 kilonewton is acting along AB, and a force of 7 kilonewton acts along AD. Okay, so force of B magnitude is 5 kilonewton, and the force that acts along CD is 7 kilonewton. So this is given. What we want is move all forces to point O. So we want to find an equivalent system that consists of a single force and a single moment that acts at O instead of these two cables. Procedure is exactly the same. That means step 1, find the resultant force and place it at this new point. How do you find the resultant? In this case, you need to write everything in vectorial form, right? So force in AB, or force at AB, is 5 kilonewton given times the unit vector, which unit vector is what? Tip minus tail divided by the length. So you have A is just 0, 0, 8. So that'll be what? 0 minus 0, 6 minus 0, I, 0 minus 8, K, divided by 36 plus 64, square root of that. This is 10. So that'll be 3I minus 4K. So that's the equation for that force. Force CD would be magnitude of the force times the unit vector. So again, this minus that. C is 0, 0, 6. So you have 2 minus 0, 2I, minus 0 minus 0 minus 3J, 0 minus 6K, divided by 4 plus 9 plus 36. Okay, this is 49, so it would be 7. So the outcome is 2I minus 3J minus 6K. Yes?
For the FAB, is it 3J?
AB is
3J.
3. Yes. I was even confused myself. This is Y, it's not J. So it's not I. So this is 6J. Thanks for noticing it. Yes. Okay. So the resultant is what? Resultant, sum of forces. Just add them up, right? So you have 2I. Okay, 3J and 3J cancel out, so I have minus 10K. So that is the resultant force, which means what you do, you just simply remove those forces, right? Put the resultant here, and that resultant is what? Is a 2 kilonewton here, and negative 10, meaning a 10 kilonewton here. However, by moving those forces, or the resultant to point O, you need to find the moment of each force about point O and add it to that location. So how do you find the moment of each force? And add them up. So would be what? You just simply find the moment of each force and add them up. Summation of moments means moment of F AB plus moment of FCD, right? Which means what? For the first moment, we need to define a position vector connecting that point anywhere along this force. I choose this as the position vector, R1. For this other force, I consider this as the position vector. So this would be simply R1 cross F of AB, right? Plus R2 cross F of CD. That means what? It's very easy because those position vectors are special cases. R1 is simply 0, 6, 0. This is the equation for the force, so 0, 3, negative 4. So that's the moment for the first force, about point O. Plus, how about this one? I, J, K. Position vector is R2, which is simply 6K. So 0, 0, 6, and this is the force, 2, negative 3, negative 6. Expand these two, add them up, and you end up with this, negative 6I plus 12J. So that would be kilonewton meter. Which means then that by moving these forces to point O, you have to add also a moment there, which is what? A component of 6 kilonewton meter in the negative direction of X. And you remember, we show moment with a double-headed arrow. So this is 6 kilonewton meter and a component of 12 kilonewton meter along Y. This is 12 kilonewton meter. So this system, which consists of these forces and moments placed at point O, does exactly the same thing that those two cables that are attached to this pole would do. We can remove them, put a force here, put this moment here, the structure will stay the same. Any questions?
So
Yes.
those moments, so the way you draw the arrows is like, it's like right-hand rule? Or?
Right-hand rule,
Right,
yes,
okay.
yes. So in other words, this is acting, rotating the structure this way. This is also rotating in this way. Right, yes. Any other questions? Or as you derive, of course, the vector equation, you find the signs anyway. So you know it is acting, for instance, in the negative direction of X, right? Or positive direction of Y. Yes?
I'm confused. Why did we find the resultant? Why couldn't we just go straight from finding the two forces and then adding the moments? What was the point of finding the result?
Yeah, we find the two forces, right? But you want to have a single force here and a single moment. Single force means the resultant of the forces, right? Forces can be replaced by a single force, which is the resultant, right? Resultant is summation of all the forces. And I forgot to put the step number here. So step number one was finding the resultant force, put it there. And step number 2 was find the moment of each force about that new point, add them all up, put it there, which is what we did. Any other questions? I'll do another problem, and which is basically the same concept. As I referred to it, I called it type 2 problem. Concept is the same, but sometimes you come across problems that are stated like that. So I just thought to give you a problem like this. I don't want you to get confused because the concept is exactly the same. Yes?
So when it's in 2D and you find the moment, it's just like the number with the direction. It's not
Correct.
in components, but when it's in 3D, you need
You mean as far as the moment, you're talking about moment or the?
Moment.
Yes, because in 2D, all moments are acting perpendicular to the plane of x, y. But they're either along the z direction, the positive direction of z, or negative direction, which means either they're clockwise or counterclockwise. That's why 2D is so much easier, because all you need to worry about is just adding up the magnitude considering the algebraic sign, which is clockwise negative, counterclockwise positive. Any other questions? Let me do another problem, and this would be also interesting. Let's say you have a beam again, AB, and these dimensions are given: 5 feet, 3 feet, 2 feet, 4 feet. And several loads are acting on this structure. This load is 500 pounds. The slope is given 3, 4, 5. There's another load of 200 pounds downward at this location, and a force of 260 pounds with, again, the slope given as 5, 12, 13. Okay? Problem statement is slightly different. In this problem, you've been asked to move all forces to a point along the direction of AB, where you will not have any moment. Problem is basically the same, but it's a little bit twisted. You've been asked to find again an equivalent system by moving these forces, in this case, to a point, let's say point O. We don't know what the location of that point is. Let's say it is located at distance x from A. But what we know is that if you move all these forces to point O, the resultant moment from this action would be 0. So you treat the problem exactly the same. Step 1, okay? Step 1, find the resultant and place it there. There is point O, which we don't know exact location of it. But that's the first step. Nothing changes. Of course, again, remember the first thing you do, always resolve these forces into their components. Okay? Remember Mr. St. Verignon. Okay? So this is 513 of 260, so that would be 100 pounds. This is 1213 of this, so 1213 of 260 would be 240 pounds. Okay? So this one is 4/5, so it would be 400. This is 3/5, would be 150, right? Oh, I'm sorry, 300. So these are the components. So just add up the x components. Would be, if this is x, this is y. You have 100 positive, negative 400, and that's it. So the total force along x-axis is 300 in the negative direction. Summation of forces along y. Okay. This is negative, negative 240. negative 200, and negative 300. That's it. So you have negative 740 pounds in y direction. So what it means is, okay, you just simply move all these forces to point O, and at that point O, which is a distance x from this end, you have a force of 300 this way and 740 this way, right? But remember, we know that the action of moving these forces to that point results in moments that we have to add them up and put it there. But in this case, we know that when we add up these moments, those moments, or their summation, would end up to be 0. Nevertheless, we follow the same procedure, right? So step 2. We just assume that we know where that point is. So we find the moment of each force about that point. So let's just start with this force of 240. Acts clockwise, the distance from here to this point, this distance is what? 10 minus x. That's all. So you have a moment of negative 240 times 10 minus x. Okay? How about this one? Moment of this force about point point O would be this distance, which is 8 minus x. So you have negative 200 times 8 minus x. How about this force? It has a moment, 300 times this distance, and this distance is what? 5 minus x. So you have negative 300 times 5 minus x. This is the moment that we should put at point O. But we are told that this moment is 0, because that's what the problem was asking us. Find this location in such a way that after we move all these forces, put the resultant there, the moment that results from this action, which means some of the moments about that point would be 0, and so if this is 0, this will give us a value for x of 7.4 feet. In other words, if we put all these forces at a point which is 7.4 feet from the left end, you only have a single force and no more. Same problem, a little bit twisted, slightly different. Any questions? Okay. Let's see now. As I promised you, you remember what I promised you at the beginning. What did I promise you? When we started the course, I said statics is about what? Anybody remember? What is static about?
Forces in equilibrium.
Forces and the action of forces on bodies, right? That's what we said. We said statics is to study forces and the action of forces on rigid bodies. We've learned everything we wanted to know about forces. What did we learn? We learned what is a translational action of a force, how you represent that in 3D with a vector equation. In 2D is just basically the components. We learned about the rotational action of a force, meaning the moment that a force causes. We also learned, most importantly, that forces acting on an object. Don't move it. We're talking about statics. So all objects, all particles that we consider in statics subjected to forces, they stay in equilibrium, right? The concept of equivalent systems, basically, if you want to interpret that, this is what it basically teaches us. That if you have tons of forces acting in a body, right, the action of all these forces is reduced to a single force and a single moment, right? But what we have not done so far is we have only looked at external forces acting on an object, okay? So what is rigid body equilibrium? Rigid body equilibrium, which is what we want to now study in the rest of the course, okay, is nothing but studying the action of forces on objects, okay? And everything that I said we wanted to know about rigid body equilibrium or the entire course of statics, we've already learned that, those basic concepts of forces and moments and equilibrium, okay? So what is the objective of the rest of the course? A rigid body, okay, which means any structure in the world that you consider, whether it's a tree supported by its roots, this board connected to the wall by some screws, or that light fixture supported by those cables that attach that to the ceiling, okay? Any structure in the world, okay, is subjected to two types of forces, okay? External or externally applied or known forces or moments. So this is the first type of load that a structure is subjected to, okay? And any structure you consider in the world, besides the fact that it is subjected to some external forces, a tree subject to the wind load, the chair you're sitting on is subjected to your body weight, that table is subjected to whatever we put on that platform. Besides those forces act externally on that object, any object in the world is supported, is fixed to another body, right? Or another object, or to some environment, okay? That's fixed or support. For instance, this table is supported by those legs, right? Those legs are basically are sitting on the floor. The chair you're sitting on is supported by those legs that are sitting on the floor. This table is supported by these bolts that are connecting it to this wall. So any rigid body, besides being subjected to some externally applied loads that we know what those are, it is also supported somehow to the rest of the environment. Those supports mean also forces. So any rigid body is also externally supported by forces that we call them external reaction or support forces. You cannot find any object that is basically floating and is not supported by some kind of a mechanism, okay? The objective of rigid body equilibrium, or studying the equilibrium of rigid bodies, okay? The objective is twofold. Objective number one is given the applied forces or loads, we call them loads also, and also moments, anything that is applied subjected to this structure. How to find those supports that are holding the structure in peace, okay? Find the forces at the supports, okay? Or forces that hold the structure in its position. So that is the objective number one in statics. Okay? Objective number two is this. Any structure you can think of in the world is made of components. Every rigid body equilibrium, every rigid body is made of components, including your own body. If you assume that your body is, of course, rigid, you have head, you have arms, you have legs. I mean, these are pieces that are put together through some connections. That chair you're sitting on is made of those legs, the piece that you're sitting on it, the seat, that platform that you put your stuff on it. All these pieces are connected together. This table is made of those legs, that top platform, this light fixture is made of that basically fixtures, those cables. All these, anything you can imagine in the world, any body, any object is made of components. As an engineer, when you want to design this system, you want to design a chair that you're sitting on, the first thing you want to know, besides of course your load that is acting on that, okay, if I put my arm on this platform that you ride on it, that is connected to the rest of the chair. So in that connection, which is basically a bolt, what kind of a bolt should I use? So in other words, you need to know what force is acting at that connection, which is that bolt. So for design of any structure, besides finding out what forces externally overall act on the structure and holding it in place, we also want to know internally what forces developing the structure, so when we are designing this, we know how to put these pieces together. So the second objective is find forces at points of connection of pieces or components of that rigid body. So that's what we will be doing rest of this course. First, we will focus on finding the external reaction forces or the support forces. Obviously, I'm sure you're going to say, well, there are hundreds or millions or gazillion types of structures and each may be supported differently. How in the world I'm going to find these external reaction forces for every structure that you can imagine? Okay? So we simplify the world as engineers, right? Regardless of what kind of support, whether it's a bolt, whether it's the leg of that chair, whether it's the root of that tree, or the foundation of this building, we look at those supports and what kind of motion they are preventing, meaning that what kind of forces or moments they're representing. And we categorize these connections, these external support, according to that. So in order to do this, to the support, okay, first of all, we look at two-dimensional structures and three-dimensional structures. And as an engineer, we come up with a model that represents the action of these supports. Since we are going to continue, of course, this next time, just let me give you an idea. Okay? Let's say you have a light pole. Okay? fixed to the ground, inserted to the ground, you poured concrete here. Let's for the time being assume this is a 2D structure. Or there's a tree, okay? Roots of this tree are supporting this structure, okay? This is what we want to know. Knowing that we have loads acting on this structure, say this is wind blowing, weight of this tree, and so on. We know these, okay? Can we find out, given these loads, what are the forces that are holding the structure in place? In order to do that, we will model or come up with a way to translate these kinds of support to what we know. The only thing we've learned, forces and moments. What does that mean? For instance, I look at this structure, it's 2D, and I say, if this is fixed, and I try to apply these loads, this cannot move in this direction, right? It cannot move in this direction, and it cannot rotate either. What does that mean? That means, therefore, there is an unknown force here in this direction that is holding it. There's an unknown force here that is holding it this way, and there's an unknown moment that is preventing this from rotation. These are the forces that we want to find, and we will see how to do it, both in 2D and 3D. So with that said, see you next time.